Hey everyone. Today we'll talk about how we leverage ClickHouse vector search capabilities for merchant matching at RAM. And since we're not in the room today, I feel like I need to probably introduce ourselves a little more. So here's Peyton. Peyton lives in Denver. He manages data platform machine learning infrastructure at Ramp, but also manages two kids at home. A random fact is that he truly enjoys resolving occasionally confusing AWS or Terraform issues that may scare everyone but him. Then about myself, I live in Calgary, Canada. I like basically using and abusing the data platform that Peyton builds, fine-tune models, and sometimes break that infrastructure. Random fact, I do have a decent tolerance to cold weather, and I moved from the coldest country in the world to settle permanently in the second coldest country in the world. That out of the way, let's talk about merchant matching. So the problem here is essentially in identifying a merchant shortly after a card transaction is attempted. So generally, the flow is the following: you swipe your card, we receive this really interesting JSON from the payment processor. This JSON sometimes carry a lot of information about where the card transaction happened, sometimes very little. Nevertheless, we need to use it somehow and map to our internal representation of a merchant. So we could then nicely display it to you on either in the app on your phone or on the web platform. So why is this a problem that's worth solving and kind of iterating on? First of all, two facts. Fact number one, payment systems actually don't send a unique, unambiguous identifier of a merchant. And as a result, this actually creates an interesting space of startups whose job is to provide what they call transaction enrichment. However, fact number two, we rely on correct information about the merchant for multiple purposes, such as reporting, for example, to show you how much you spend per merchant, and we need to unify different services purchased under the same merchant into like one entity. Then card restrictions and policy. For example, at the time of the swipe, we need to check if this transaction is with Starbucks and allow it, or if it's with Costco, and for example, you set up a restriction on the card to decline Costco transactions, and we want to make sure that Costco transaction is properly declined. And then finally, we want to tailor onboarding experiences for you by essentially learning from your spend patterns early. And that way we can recommend and cross-sell you different kind of products on Ramp. How can we resolve this problem potentially? So there's kind of multiple ways ranked differently in terms of their performance. So the first simple approach is rules. So we look for specific words and JSON field values. Usually that approach is a high precision and low recall. And however, it's really hard to generalize because of that low recall part, meaning that there might be millions of merchants out there, and it's hard to come up with millions of rules that would actually work. So it doesn't scale very well. Then there's kind of classic fuzzy matching heuristics, such as string distance against like previously identified transactions that already have the merchant attached. So that way, we can achieve probably a rather medium precision because heuristics, they tend to fail in kind of fun, unpredictable ways, and even more fun to debug, as probably many of you know, can definitely be applied to a larger range of transactions compared to the rules. And then obviously, fuzzy matching heuristics tend to be hard to maintain, and they lead to what we call spaghetti code. And then finally, the third approach is embeddings. In that approach, we train a model that maps a JSON that payment processor sends to a vector space. We'll discuss that in a bit. And it checks the similarity between a merchant representation in that vector space versus the new transaction. So generally, these methods have a good precision that is also tweakable, have variable recall depending on how you tweak some of the parameters, and it generalizes well, as you can see from rapid expansion of embeddings methods across multiple products, multiple services. Let's talk a little bit about training, how we basically obtain those embeddings. So basically what we do is we train an embedder, a model within this framework called metric learning. The main goal of training in metric learning framework is to turn strings into vectors such that similar transactions should be nearby in that vector space. Different merchants should be far away. So for example, in this figure, you can see that Home Depot transactions are far away from Chipotle. However, McDonald's is a little bit closer to Chipotle because they're both fast food. And then Domino's and Little Caesars, they kind of really overlap because they both sell pizza. And then also another property is that we can use these vectors in the embedding space and apply some kind of common distance metric to quantify the similarity between different merchants. In this particular example, in our particular example, the out-of-the-box solutions, they tend to fail, mostly because the data domain is quite specific. It's neither a truly semantic similarity nor really symbolic similarity. It's kind of something in between with somewhat partially matching sequences that could be a powerful signal. So it's kind of like a mix. So that's why metric learning is important here. So specifically, we used this library called sentence transformers that uses PyTorch under the hood and trained our encoders using this thing called triplet loss. So the triplet loss essentially aims at moving, again, similar transactions together from the same merchant, and transactions from different merchants, it tries to move them apart. So as you see in the figure, if, say, McDonald's and Amazon transactions happen to be closed before the training, after the training, they kind of move apart, and instead Burger King transactions come closer to McDonald's, in simple words. So we also use this thing called online hard triplet mining, and I can provide kind of more nerdy details in the Q&A. It's basically essentially a way for the network to keep learning as it goes through the data set, and get more like hotter and hotter examples as it learns. And then in the end, we represent a merchant essentially as a center of its all transactions. So if you think about after we map these transactions from strings into a vector, say all transactions from McDonald's, we can represent McDonald's as an average vector, what we call a centroid of that cluster. And then finally, how do we validate this? We basically backtest the whole thing, very similar to how we would observe this model perform in a production setting. Basically, what we do is we will fix the corpus of merchants and then start streaming a set of transactions. And what we care really about is what we call action accuracy, meaning that we would like to reward correct matches or correct absence of matches, meaning that here's a new transaction. It truly is from a new merchant. We don't have anything to match it to. Therefore, we need to create a new merchant. And then we also penalize mismatches. So we receive a transaction from Burger King, mapped it to McDonald's, but we need to penalize that. And then we also penalize failure when a match is present, but we essentially couldn't find it. And with that, I'll pass it to Peyton to talk about how we populate embeddings.
Hey everyone, as Anton said, I'm Peyton, and it is nice to see everybody. I hope everyone is having a good time so far, and thank you for coming out. Great. So Anton talked about how we can represent transactions with embeddings. So how do we actually map those transactions to merchants? How do we obtain like a merchant embedding? Well, whenever we receive a transaction, we generate an embedding for that. So this is a call out to a machine learning service that we host. And we pass that data like you see below. That looks pretty cryptic if you look at it just kind of with your own eyes. But we can take that and generate an embedding with it. And then we can store it in ClickHouse. And we do this via Kafka, essentially. So whenever somebody swipes a card or makes a transaction, then we can call it to the service kind of in the background to get an embedding and then store that embedding. And then once we have lots of embeddings, then periodically we have an Airflow job that gets all the embeddings from a merchant and simply averages them. So you can think of a big cloud of transaction embeddings. And for a given merchant, we take kind of the average of that and we get a centroid. And we write that to a table in ClickHouse that we can later reference. And you'll see what we do with that here in a moment. That's the training, that's the building the embeddings. But how do we actually use them in production? So if I go and swipe my card, how do we actually map that to a merchant in real time or more or less real time? Well, previously, we basically, when a transaction occurs, we looked at it and applied a few heuristics and rules. And the most basic was, does this look like something we've seen before? Like, is it mostly the same? Have we seen this exact same thing before? If so, great. We're pretty sure it's a given merchant. Use that merchant. If not, then this is the kind of area that we wanted to build upon. In the past, we used an increasingly desperate set of heuristics to kind of match transactions to merchants, like in the case where things didn't look too similar on the surface. But as we grow, this became more problematic. You can imagine the number of transactions we've seen has grown a lot over time, and we have a lot of strange-looking data. And so this provides us with an opportunity to use our new approach here. So given that a given transaction doesn't look like something we've seen before, at least kind of on the surface, it's not an easy win, we can generate an embedding. And then we can take that embedding, we can go look for other transactions with that embedding or other merchants with that embedding using nearest neighbors, basically. And if it's close enough, if it meets a certain threshold, then hey, we found a merchant using our nearest neighbors approach. Pretty simple. If not, then we can try something else. We'll get to that in a moment. And so what it looks like is that when we get a transaction, we go to our database and we say, hey, have we seen something like this before? Often the answer is yes. Sometimes the answer is no. And so then we have to reach out to our embedding service and generate embeddings for the transaction. We give it some card acceptor data that Anton kind of demonstrated. And we get basically a vector of numbers back. And then we can take that vector of numbers, give it to ClickHouse and say, hey, find me the closest transactions or find me the closest merchants and let's look at them. And ClickHouse will return those. Certainly, we didn't think, coming into this, that ClickHouse, it's not top of mind when you think of like vector searches in a lot of contexts, but certainly found the capabilities to be pretty robust here, and pretty capable. Right, so now we have this new algorithm that I've described. How do we actually get it into production? You can imagine that we want to be careful here. Rant values velocity. We want to ship fast. We want to build new features, build new products as quickly as possible. But we want to value quality as well. And we can't just kind of take this new strategy and flick a switch and have everything start using it all of a sudden. So what we did was essentially we asynchronously try every rule, every heuristic, every strategy for a given transaction, regardless of what decision we actually make. So somebody swipes a card and maybe it matches right off the bat to some heuristic that's very fast. Maybe we've seen something just like it before. Nonetheless, we record kind of what it would return using our new algorithm, and we save that for analysis. That way, when we're ready to kind of flick the switch and send traffic to our new algorithm, we can be confident that we're not going to break anything, which is very important, you can imagine. That said, we can do better still. So if you kind of followed along, there's the case where we don't find a nearest neighbor. Maybe the score is too low. Maybe the nearest merchant is actually quite a distance away. If you kind of map this in vector space. So what do? Well, we try something else. And that something else is we use an LLM to help us out here. We take that transaction, we take similar transactions, and we feed it to an LLM to kind of give us a hint. Use its own kind of intelligence to figure out, okay, what transactions are similar to this transaction, even kind of outside of the vector space that we generate the embeddings in. And if that matches close, then great, we have a new source for merchant. If not, then we create a new merchant. This is something we haven't seen before. So zooming out, this is what the whole algorithm looks like that we use ClickHouse for. It's quite a lot. You probably can't read the text on the screen if you're sitting far back, but this is it. That said, we can do better still. A lot of merchants like Amazon, for example, they have a lot of transactions, and those transactions don't necessarily look the same. So here you have a big kind of cloud here with the red X in the middle as a centroid. If you take a new kind of data point, it might not look very similar to that centroid, but it might look very similar to some of those transactions on the edge. And so Anton had the bright idea of how about we break this down into mini centroids to get better and better matches. And this is one example of an iteration that we kind of made to make this even better. And yeah, Anton will talk about some of the results we've seen.
Yeah, so after all that said and kind of deployed, you still have to now kind of look back and see, did you improve any metric at all in the end? Because essentially you still can't tell whether all this was worth the effort or not. And again, it's somewhat hard to come up with a exhaustive set of metrics that will please everyone in the room. Your PM might want one thing, you yourself might come up with another metric, your data analyst would want a third one. Eventually, we kind of converge on this one metric, which is essentially the percent of transactions that are matched out of the transactions that were previously not matched. So basically, if you think about that as a metric, we can sort of plot its evolution over time. So on the y-axis here, the scale shows in percent the transactions that previously basically were not matched, having passed high kind of precision stages, like the early stages that Bateman showed before. So essentially, before the rollout, which is probably a little bit before the March 11th on this screen, essentially there would be everything in this pile of transactions would be unmatched. And then as we started slowly rolling out, again, we didn't come up with all optimizations on the day one, right? This was a kind of evolutionary process. So first we rolled out the regular, like the main centroids, kind of like the basic version of this algorithm. And it started eating, little bit by bit, about 25 maybe percent. You can see that gray bar kind of evolving over time until around April 12th. So a month after, we came up with this idea to now do the searches against what we call mini centroids. So like the mini clouds within the clouds. And then again, that idea needed a little bit of testing. Eventually, we rolled it out, and that helped us. That together with the regular centroid matching helped us cannibalize maybe another 15%. So now we already cut basically the mismatches by 40%. And then after that, we said, well, why not bring in LLM for like the really hard transactions, the ones that are super confusing to match, and apply RAG on the embeddings that we already have. Now, we rolled that out, and then we also started tuning the thresholds based on the accuracy to see basically how far in terms of trade-off of coverage versus accuracy we could go. And that's what allowed us in the end to reach kind of like steady state where we are about right now, which is essentially something about 75% of all the transactions that were previously not matched are now matched using this ensemble of essentially three algorithms kind of applied serially. So yeah, in the end, all of our optimizations paid dividends. That's kind of great to see. Our choice of platform for vector search also paid big dividends. We were able to essentially do really nice joins with the data that we already had in ClickHouse, but also do the vector searches at a very reasonable latency. I think the average, sorry, not the average, the P90 of our lookups kind of stabilize around 200 mils, which we found appropriate for the application. And then, yeah, in the process, we learned a lot about ClickHouse and its vector search capabilities, which was also quite gratifying. And then in the end, again, it took a whole village to get us here, and I purposely selected the most embarrassing pictures of the folks that I worked with online. So, yeah, I would definitely like to express my gratitude to all the folks that worked with me on this in Peyton, in RAM, as well as within ClickHouse. So that's kind of it. That's all we have for today.